So I'm Jian from the AST in Japan, and recently we are very interested to develop very small and low power sensor nodes, especially for animal monitoring, to monitoring the biological information of animals. And we also hope this kind of technology can be used in near future as for human, the human interface or medical care devices. So here's the outline of my presentation. First, I will explain a little bit about the background and motivations of this implantable device. We want to understand actually the activities and biological information of experimental animals, and also we want to improve the productivities of the livestock animals. And some of the results, is some preliminary results we have, but I think it's quite interesting. And finally, I will summarize my talk. Well, in the past many years, we focused on the MEMS sensor and also the integration of the MEMS with IC for especially for the size-free integration. And we tried to make, the MEMS always use the 6-8 inch wafer. For IC, we use 12 or even bigger wafers. So we try to develop a new approach for the size-free integration in large scale. And also we make the very small size, compact size, various sensor nodes. This is a temperature and humidity sensor node. The size was about 4 by 4 millimeter. And we also cooperate with some companies and try to develop this, all-in-one package sensor node. For example, this kind of sensor node we already used for infrastructure monitoring. And we hope the lifetime of the sensor node can be at least 10 years. That's why we use ceramic package, and also we make the antenna in the ceramics, and we use solar cell and also energy harvesting device. And this is also kind of energy harvesting device. This device can operate at very low frequency, like 15 to 20 hertz. But as you know, the problem is still we can have only maybe a few microwatts power. That's still quite low. And we just hope in the near future, probably, as you know, at the moment people are very interested in the industry of 4.0, and this we are talking about machine-to-machine connection. So hopefully in near future we can move to the human-to-machine in the connection, like drivers and cars. So this is why we're quite interested in the implantable device, because compared to the wearable device, this device may have more accurate data, and also don't care too much about how to wear the device. You just have a very small implanted chip in your body. That is in the future work. So at the beginning we start from experimental animals. So why we choose mouse? Because the mouse is frequently used for new medicine, for new food development, and also it's quite important to understand the nature activities of mouse. As we discussed with someone who used mouse for experiments, I'm very surprising that the maintenance cost for one mouse will be like $400 per year. And for some reason, they must check the temperature in 24 hours for maybe a few weeks. So it's quite tough work. And yeah, of course, you can have some already commercial available, implanted temperature sensor. But in that case, the sensor node is too big, so people need to use a little bit bigger, bigger animals like rats. But rats, as far as I know, the size of the rats will be 3 times of mouse, but also the maintenance cost will be also more than $1,000 per year. So that's why we try to implant very small, cheap sensor node to mouse. And we want to also try to have more accurate data from the body temperature of the mouse. And we choose cow is because, in Japan, the beef is quite good and quite expensive. As far as I know, there will be only probably 10 to 20 kilogram first grade beef from a cow. And when we discuss about the cost for cow will be like 8 to 10 US dollars, but probably 40 to 50% is from the calf is a baby cow. So that's quite important to, sorry. It's quite important to monitor the body temperature of cow for the artificial insemination control. And also for cows, it's quite important to optimize the food they give to cow. And in that case, if we give good food to cow, the lumen is the first stomach of cow. The pH value will decrease very fast. If the pH value is lower than 5.5, the cow maybe die in next few hours. So it's also quite important to monitor the lumen pH sensor. So for that research, we have another poster. The number is C9230. So per session will be held in this afternoon. So if you're interested, please visit our poster. And of course, another important is the human labor cost. The cow is about 30%. So that's why we choose mouse. For mouse, we need to develop very small size, compact sensor node. And for cow, because for mouse, for those kind of investigation, it takes maybe only a few weeks. But for cow, we hope the sensor node can stay in the cow for all the lifetime of the cow. That means maybe 2 to 3 years. And we want to also monitor not only the temperature, but also health condition of the cow and also their activities, if they have enough exercise every day. So for cow, we just care about a little bit more about the power. And this shows the structure of the sensor node. So actually, we have also customized the RFIC developed by ourselves, but in this research, when we considering the cost issue, we use the commercial available RFIC from Silicon Labs. The Silicon Labs 4010. It's a fully integrated LSI, and we use the temperature sensor from Texas Instruments. This sensor includes the temperature with a resolution of 0.03 degrees C, and also this chip has the IR temperature with a very high resolution. And we choose the frequency 923 megahertz. It's because first is the license-free frequency in Japan, and second reason is we may have very low return loss by the skin after we implant the animals. So that's why we choose this frequency. So the sensor node is itself is quite small. It's I think it's 7 by 7 millimeter, and we can make it much smaller if we use our customized LSI. But the problem is the battery. This is the smallest battery we can use, but it's only 8 milliampere hour. And we test this battery. If we measure the temperature every 10 minutes and send the data every 10 minutes, the lifetime of the battery will be like 2 to 3 weeks. So in some cases, too small battery. And we need to make program to the MCU to make it work well. And we check the power consumption. As you may say, in the sleep mode, it consumes only the microwatts power. And also in the measurement mode, it's still not so high power. But the problem is for the IR temperature, it strongly depends on the stabilization time. For example, if we have 4 seconds before the measurement, the resolution could be 0.125 degrees C, but if we have only 0.25 seconds, the resolution will be 0.5 degrees C. So this is quite important. And we also check if we include and if we not include this function in our sensor node. And for the RF irradiation power, we also check the communication distance. And for the mouse application, normally in the lab, the size of the lab will be like few meters by few meters. So we believe when the irradiation power was 0 dBm, the transmission distance is quite good enough for a mouse. But actually, after implantation, we found the distance is much longer because of the skin of the mouse is also used as the antenna, so we can have more longer transmission distance is quite good enough. And this is packaged sensor nodes. And we also check the different configurations of the antenna. As you know, this is a non-directional type, but if we use this round type, the antenna the direction will be in this direction. And this is, we test in lab, if the power of site has 0 dBm, we did not find any decrease in the communication distance. But of course, we can confirm this is directional. We need to care about the direction. But after implantation, actually in this package, the antenna is here. After implantation, because as I said, the skin of the mouse can be used also as an antenna. So that means we found it's still, okay to use any direction. It's not very sensitive to the direction. And this is a package sensor node, and we try to implant this sensor node to the mouse. The size of the mouse only 10 centimeter. So this is a sensor node. So the precision of the implantation is quite important because we found if the sensor node is too close to stomach, the mouse will die maybe in the next few days. So I think it's quite, the sensor node is better to be in the chest or close. So anyway, it's a little bit far from the stomach, it's better. And this is the monitored results. And we can find this is just after surgery. And quite important thing is, after the second day of the surgery, we have some injection to avoid any affection by the surgery. And we can notice the temperature decrease up to 32.5 degrees C. And after the next few days, the mouse will recover, so the temperature a little bit increase. And from here, we believe the mouse return to the normal activity. And you can say the mouse will be very active in the evening. So in the evening, the temperature is relatively high, about 38 degrees. But in the daytime, they stay at very low activity. So the temperature was only about 35 degrees C to 36 degrees C. I think it is quite normal when we discussed with some professors who were familiar with the animals. And this is one mouse after the implant sensor node, after 10 months after. So we can see the sensor node still here, but the mouse still alive. Until today, I think it's still alive. This is our measurement. We have antenna here, we have many mouse in the same room, so we can at the same time receive the data from many different mouse. So next step is also we just think about monitoring the activities of the mouse, because in some cases, if the mouse has stress, they will like to fight with each other. So it's very good to understand their activities after the injection some new medicine or something. And from this figure, you may say that when we think about consider the size, we use this battery. The battery lifetime can be 4 months in our life. When we think about the size, this is much bigger than sensor node, and also the weight. Because the mouse the body weight only 15 grams. So the sensor node is only 0.14 gram, but the battery will be around 1 gram. And when we also think about the volume, the weight, and the lifetime, it all depends on the battery. And another interesting thing is, as you know, we test this battery in lab, and the lifetime was about 4 months. But after implant, the lifetime was only 1 month. I think it's because the body temperature is too high. So the battery is too high. This test was under room temperature. This is at about 38 degrees C. They will shorten the lifetime to about 1 month. And also, if we use the air temperature sensor, that consumes a lot of power. And if we don't use the air temperature sensor, it's very low power. In both cases, the lifetime was just the same. It's about 1 month. So we believe it's because of the high temperature of the mouse and reduce the lifetime. And for the cow, we also think about to develop this wireless power transmission module. So in this module, we use coil to transfer the power, and we use the supercapacitor to save the energy. Because if you use battery, the charge time usually takes 30 minutes to probably 2 hours. And when we use this supercapacitor, the charge time will be only like 1 minute. We can fully charge the supercapacitor, and the power transmission efficiency can be like 70%. And this implantation results, we can find the air temperature sensor has very fast response, but actually the measured temperature is lower than the body temperature. This is because the packaging material. And this is the on-chip, on-die temperature. The very interesting thing is we found there is a little temperature increase, about 0.15 degree increase after refeeding the cow. This means because the implant position is quite close to the lumen of the cow. So that's very sensitive. We can even monitor the lumen temperature increase. And for the wireless powered module, of course, we need some improvements because the thickness of the skin of the cow is about 6 centimeters. It's much thicker than we expected. Well, and in future, we hope we can move a little bit to the human the health or the medical care, and also the human interface, the communication between human and the machines, like driver and the car. And here's the conclusion. So I think I don't need to repeat. And I want to mention that all the animals used in study was treated in accordance with the guideline for animal experiments in Japan. Thank you very much. So.